Hey everyone, this is part 2 of the volumes by cross-section. The last video ended on the first example of cross-sections of semicircles. This one we are going to take squares, okay? And the key here is we're going to be perpendicular to the y-axis. And if we chop perpendicular to the y-axis, that's going to give us a square. So that is why whenever you do this in your notebook, so remember this is your y-axis, for example, here. And what would perpendicular to the y-axis look like? That'd be like this. So imagine you're taking your knife, here's your handle, and you're chopping like this, and you end up with squares. So make sure they're going horizontally, not vertically, in your notebook whenever you glue these things down. Before we do this problem, I just want to show you two different brief visuals of what it looks like if you add up infinitely many squares, what a volume looks like. Unfortunately, Geometry Sketchpad, again, doesn't have exactly what I want. It doesn't have the square root of x base that we're really looking for, which would be right here. And they also are doing this one vertically, and we're doing it horizontally. But just watch quick so you can see, like, what does it look like to have a square cross-section? So I'm taking, I'm taking my base, and I'm just kind of laying it flat here to help you see it. And what if I took squares here? I remember this thing really looks like this, but we're laying it flat so you can see it better. And squares are coming up out of your base. So the squares are largest wherever the distance is the furthest, and they're smaller on the edges here. So let's go ahead and create a solid. Woo! All right, look at that. So this is what this would look like if I took squares and ran them from left to right here. And let's actually show our solid with the squares in the middle. So here's one example. And different views of it. Okay, there's that one. That was fun. Let's look at this one from a previous FRQ. I'm just going to let this one run through real quick so you can see. Again, this kind of looks like a square root of x shape. Again, the problem is we are not doing it horizontally. This one is still vertically, but it helps you see it. So here's the base. We're laying it down flat so you can imagine like your notebook is down flat on your paper. Notice the square edge length is small and then it's large. There's the largest, there it gets small again. So you can look at it from either view. That's what your square looks like. And this is the top view is showing you the edge getting larger and larger and then smaller. And this is like literally what the square looks like coming up out. And one more time, here's how you can get an actual volume. And here's one more view of it. Whoop. All right, cool. So let's go ahead and try one. The thing is, we're chopping it horizontally, like it said. So let's see what that would look like. It's going to be a little bit different than the one we just did, but you already know how to deal with a horizontal distance. All right, so what we're imagining here is I'm going to draw a random square coming up out of my paper. So you could have one that looks here, or if you cut it all the way down here, it'd be like a way bigger square. But let's just look at this one up here. All right, so again, we always start with edge. Just like before, it's the same process. Start with one random edge of our square, and you need to find the length of that. All right, so here's a length on my base. Okay, here's the base. Usually it's going to be called R, the region. So this is a horizontal distance. So remember, distance between 2 points, video notes. To find the distance of a horizontal line segment, you're going to subtract x values, and you're going to go from right minus left because we want to end up with like a positive value. So do this one minus this one. Okay, so let's subtract our x's. So here's the deal. On this side, like this edge is getting smaller and smaller and smaller. So your expression for the edge should have a variable in it. It's not going to be constant. So what is the x value here? Well, the x value on this side is always the x value of 2. What is the x value here? Well, or here, well, that's on this function, which is y equals square root of x, but I need to rewrite it, just like that video shows you, distance between 2 points. You have to rewrite and solve this function for x. So if you have y equals x, or if you have y equals square root of x, I'm going to square each side. So then you have y squared equals x. So the x value on here is x equals y squared. Okay, so let's subtract our x values. Whoop. What that would look like is we would do 2 minus y squared. So the x value here is 2. The x value here is y squared. All right, so that gives you the edge length of a random square. So then you go from the edge length of a square to now we need the area of a general shape. So the area of a square is side squared, but let's actually personalize this for our specific square where the side S was this. So in our case, we have 2 minus y squared squared because this is a side length. So we're doing side squared. All right, so I got the edge length, I got the area of one of my random squares, and how many of these squares do we need? We need infinitely many squares, so that's where my integrals come in because I'm adding up infinitely many areas in quotes because they're really volumes. So, all right, here's the deal. If I'm going to add up infinitely many of these, and I'm going to put this here, 2 minus y squared squared. This right here is the area side squared. Okay. If your sentence is about y, your sentence needs to end in y because your square here has a tiny, tiny width dy going up and down now. And your sentence needs to begin with y. So I'm going to chop, chop, chop starting down here at this y value. And going up, your y values are increasing. Chop, 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 all the way to here. All right, so when x is 2, plug 2 into this function. The function at 2 is square root of 2. So that y value here is square root of 2. All right, so going from y equals 0 to y equals square root of 2. Before I can go ahead and do an antiderivative, I need to rewrite 2 minus y squared squared. So that's going to involve some foiling here. So that's going to look like 4 minus 4y squared plus y to the 4th. Whenever I 2 times 2 is 4, and then keep foiling here, you end up with this dy. All right, antiderivative time. Remember, everything is like in terms of y. So the antiderivative of 4 is 4y minus 4y cubed over 3 plus y to the 5th over 5 from 0 to root 2. Okay, let's keep going here. This would be 4 root 2 minus 4 times root 2 cubed over 3 plus root 2 to the 5th over 5. Well, this is getting kind of ugly. Minus, plug 0 in. They all have a y, so it's just one big 0. All right, so, I mean, you could rewrite this one more time. It'd be 4 root 2 minus 4 thirds. You could write this as 2 root 2. And then plus, you could write this as 1/5. And then root 2 times root 2 times root 2 times root 2 is 4 with another root 2. Like you could keep going. But on the AP exam, you can stop here. So stop here. Or you could stop actually here on a FRQ. Like you don't have to keep going. If this was a no calculator problem, don't waste time trying to simplify any more than you need to. All right, cool. That was our square. So let's go ahead and do our triangle. So if you haven't built your triangles, can you pause your video and get your base drawn and go ahead and anchor down your triangles? So for this last problem, one more, we are going to imagine that we have, okay, same region R, cross sections cut by planes perpendicular to the x-axis. They are isosceles right triangles. Now here's the thing, ready? One leg on the base. So let's break this down here and see what on earth is going on. First of all, I'm perpendicular to the x-axis. So here is our x-axis. We're going to be perpendicular to it. So like this. That is why your triangles are coming up out of the paper like so. It's easier to see on your notebook when the things are actually sticking up out of your paper than like to try and draw it two-dimensionally. And I have one leg on the base. So let's take this one triangle right here and let's redraw it here. Now this thing is isosceles, okay? So here's your hypotenuse. They're not saying a hypotenuse is on the base. They're saying a leg is on the base. So whatever distance this leg is, this leg that's coming up out of the paper, that one's right here, that's going to be congruent to this. Like they're the same length. Okay, so keep that in mind. Whoop. All right, so I tried my best to draw it right here. Here's the hypotenuse right there. This is one edge length. Remember, we always start with one edge that's on the base. And then however far that distance is, it's the same distance coming up out of our paper because, again, it is isosceles. All right, so I have a visual to show you here. Last visual of the video. And that visual that I want to show you, is this one. Circles with isosceles right triangles. Okay, so let's look and see what it looks like whenever you have right triangles that are isosceles coming up out of the paper. So we're chopping this thing vertically, which we're about to do. Again, I know it's a circular base. We have a square root base, but just watch. I'm dropping it flat. Again, your notebook is flat on your desk. These are what the triangles look like coming up out of the paper. So they're isosceles. So this distance is the same as the distance coming up. And again, it really looks like that, but we dropped it flat. And let's sweep our triangle. Our triangle gets larger and larger, and then it's going to get smaller as the edge shortens, like that. And let's go ahead and create a solid out of this. So this is how you can get an actual 3D shape coming up off of your paper. Like that. And here's what our solid looks like. There's triangles within it. And if you rotate this thing, it isn't a perfect visual, but it kind of helps you see what's going on. All right, so let's go ahead and we're going to do the same process as before. We always start by finding the edge length. Okay, so an edge is line on your base, which is right here. So again, the base is not the hypotenuse. So to find the distance of this vertical line, distance between 2 points video, you're going to subtract your y value. So what's the y value up here? It's on the curve, which is changing. It's square root of x. And what's the y value down here? It's not changing. It's always 0. So we're going to subtract those. So that'd be the square root of x minus 0 is the square root of x. So this distance, no matter where you draw it, like wherever your triangles are coming up out of that paper, that distance of this leg is always square root of x. All right, so then we're going to get the area of a general shape, just like before. So I'm going to use my edge length to get an area. All right, so I'm dealing with a triangle here, right? So the area of a triangle, we're not adding up infinitely many circles or semicircles, we're adding up infinitely many triangles. So the area of a random triangle is 1/2 base times height. So 1/2, okay, what is my base? My base was this, which is right here. That we found to be square root of x. The height is the same thing because it's isosceles, so it's also square root of x. So that means the area of a random triangle on my base is 1/2 x. How many triangles do we want? We want infinitely many triangles. We're going to add them up. We're going to use an integral to add up infinitely many. And we're chopping vertically. So our triangles start on the left here at x equals 0. Chop, all the way to 2. So start at x equals 0, end at x equals 2. So we're going to do the sum of infinitely many areas, but we're going to really turn them into volumes. So that means I'm going to take my expression for a random area, and I'm going to put it right here, and let's just add them up. So this is an area, and then to make it a volume, what do I need? I need a tiny dx, the width. So put a dx on it, and now I have a volume. Isn't that amazing? So x equals 0 to x equals 2. So this just should be an easy antiderivative, right? Antiderivative of x dx. So I'm going to do 1/2 times x squared over 2 from 0 to 2. So I have 1/4 x squared from 0 to 2. So what would that be? 1/4 times 2 squared minus 1/4 times 0. That's gone. 2 squared is 4. 4 over 4 is 1. The volume of this shape coming out of the paper, is 1. Okay, cool. Come to class with your volumes built. Make sure they're taped down, and we will continue in class with more volumes.